So, good evening. It's a pleasure and an honor to look at you. We have Linda Spilker with us, who's a planetologist specialized in exoplanets and who's responsible, scientific manager for this fabulous mission. Just a few elements by way of an introduction concerning the purpose of the Saturn study, and in particular the role of the French community, and more specifically the Toulouse community in this mission. Let's situate the planets in our solar system, first of all. Here we have all of the planets in their order of distance in relation to the Sun. Here you've got the respective sizes, which are respected here, but the distances, obviously, have been completely compressed. We have our Earth here, which is by definition at 1 astronomic unit from the Sun. 1 astronomic unit is 150 million kilometers, and the Moon here, you can see, the Saturn is at 10 astronomic units, which gives you an idea of the distances in our solar system. And we can classify planets into 2 main categories. Telluric planets, Mercury, Venus, the Earth and Mars, because these are planets with a solid surface. And then we have gaseous planets, which are giant planets like Jupiter, Saturn, Uranus and Neptune. So these are planets that don't have a solid surface. They're balls of compressed gas, but they just have a solid nucleus. NASA prepared the mission with Pioneer and Voyager to study these giant planets right from the 1970s. We had the Pioneer mission, first of all, 10 and 11, which from 1972 started to travel into our solar system with a quick flyby over these planets, with the famous salutation from humanity and our civilization, in case the probes are actually captured by other civilizations out in space. Then in 1977, we had the Voyager 1 mission with the Voyager probes 1 and 2, with instrumentation which was much more sophisticated, but that was also just flew over the planets. And this gave us the possibility to discover the nature of these objects, but also, of course, it raised a large number of questions. It raised more questions than it actually provided responses. So it's in this context that the Cassini mission was born in the 90s. And the idea here was to have a probe that was going to go into orbit around Saturn to study this mysterious planet with its rings. And as far as the objectives were concerned scientifically, we had 4 main categories. First of all, to study Saturn and its rings. Here we have an image of Saturn taken by the Voyager probe, and you can see the definition is not that good. Later, Linda will show us some images taken by Cassini, and here you're going to see something, you're going to really see the difference there. We have Titan, which is the biggest satellite of Saturn, and also the satellites. It has the densest atmosphere of any planet in the solar system. This is something which is quite enigmatic. You can't see the surface here because it's covered by this atmospheric veil. But it's a very enigmatic satellite too, because its atmosphere resembles the biotic atmosphere of the Earth. And in other words, an atmosphere which suggests that it's rather like the Earth's atmosphere before the emergence of life. It's very dense, and it contains a lot of hydrocarbons. Next, we have the ice satellites. These are very enigmatic objects, again, very mysterious. And as we'll see later, we had a number of surprises with Cassini when it came to looking at these objects. And then we have the 4th major category of scientific objectives, which concern the magnetosphere of Saturn. This is a big magnetic bubble formed by an interaction between the solar wind coming in here and the magnetic field of the planet. And you have ionized gas here, which is trapped in this magnetosphere. And this leads to phenomena like magnetic storms of the sort we encounter on Earth too. The Cassini mission had 2 major components. First of all, the Saturn orbiter, that was put into orbit around Saturn for a number of years. Then we had the Huygens probe, which was detached from the orbiter and entered onto the surface of Titan. The Cassini mission was also a brilliant example of cooperation between the major space agencies. NASA was responsible for the Saturn orbiter, and the European Space Agency ESA was responsible for the Huygens probe, which entered into Titan's atmosphere. And looking at these experiments, both on the orbiter and on the Huygens probe, there was a component that was multinational. We had the Americans and the Europeans that were investigating this together, both on the probe and mother probe and the daughter probe, as we'll see later. But let's start off with the European component, and in particular the Huygens probe. Here we have a photo of the probe being assembled. It was actually prepared by Aérospatiale at the time in Cannes. Now Aérospatiale forms part of the Airbus group, and here we can see the sequence of entry into the atmosphere of Titan by parachute and landing. So these experiments on the Huygens probe, one in particular, there were experiments on the possibility that were conducted by the French. First of all, the Huygens atmospheric structure instrument, which had several sensors to see what the characteristics of Titan's atmosphere were. For example, what was the pressure, what was the temperature, what was the electrical conductivity. This was prepared by Lézier in Paris, and then there was the aerosol collector and paralyzer, which was developed by Latmos, again in Paris, which took the aerosols, in other words, the small particles from Titan's atmosphere, and to break them down and study their composition. Next, we had the orbiter. On orbiter, we had 12 experiments. It's rather like when we want to discover a new object, we bring into contribution all of our senses, vision, hearing, touch, and these are all complementary sources of data which our sensors give us to understand the object. The same applies to a planetary probe like Cassini, where we have cameras, we've got spectrometers, magnetometers, we have particle detectors, and we'll see now what the French contribution with these 6 experiments. There was the plasma spectrometer, which is an experiment under the responsibility of the Americans with the Southwest Research Institute, but we also had a French contribution from Latmos in Paris. And this is an instrument to measure the plasma, in other words, the ionized gas in the magnetosphere. We had the imaging science subsystem with a set of cameras on board Cassini. Again, an American instrument here, but here with the contribution from CNES, and in particular, CNES provided the electronic modules enabling us to do image decompression, and it's thanks to these electronic modules that we're able to compress the images to send them by telemetry and have a flow of images that was extremely satisfactory. We also had spectrometers, infrared spectrometers, provided by NASA with a contribution from the CEA, the Atomic Energy Commission, and the other visible infrared mapping spectrometer under the main responsibility of the University of Arizona, but also with a contribution from Lézier. We also had a radio and plasma wave spectrometer with a contribution again from Latmos. So we had these experiments. If we look at this, we can see that there are just 5 here. What happened with the 6th experiment? This was an experiment that had a special role here for us in Toulouse because we contributed to its development. This was the MIMI experiment. This means magnetospheric imaging instrument. Under the Americans' responsibility, this is the Johns Ford University, which was mainly responsible for developing this experiment, with a contribution from the Germans and also from the French in particular. CSR, this is the Space Research Center, the laboratory which then became IRAP, the Astrophysics and Planetology Research Institute in Toulouse. And with my team in Toulouse here, we developed the onboard electronics for this particular experiment. So the development of this experiment was a technical feat. It was a scientific feat too, because we had to prepare it in the scientific context for the measurements we're going to be doing. But it's also a human adventure. A human adventure. I'll just show you a quick photo of my team, the international team behind this experiment, with the two prime instigators, Tom Mikis and John Mitchell, who came to Toulouse as part of an international symposium at the time. And what was Toulouse's role here? Obviously to develop the instrument, but also to prepare the scientific context. One of the studies we conducted in Toulouse, I'll show you just an example of this to hand over to Linda afterwards. This was the interaction between Titan and the Saturn magnetosphere. We didn't know what it was going to look like, so with the CSR, we developed a model, and we studied the laws of physics here and used mathematical equations to try and define what this interaction actually was with this half moon on the right of Titan. And so this was worked on at CNRS in our discipline. This gave us an idea of the scale of time. And then, obviously, we had the first flybys of Cassini. And here we were surprised because we were able to confirm that there is indeed this this crescent, this moon crescent, and it was much richer than what we'd seen before with Cassini. In particular, these were studies that we conducted with Philippe Garnier, who was preparing his thesis at the time to do physical measurements at Toulouse here. And this enabled us to understand how the higher atmosphere of Titan diffuses into space. Since then, the investigation in Toulouse was developed. In particular, we had 4 experiments in which we're very active in Toulouse. First of all, the MIMI, which I was talking about, the Cassini plasma spectrometer from CAPS, the ultraviolet imaging spectrograph, and also the experiment into plasma waves. And right in the middle here, we have a very special role. This is the role of interdisciplinary science, which coordinates the different teams working in the different disciplines to ensure the best possible synergy. And this is run largely through Michel Blanc, who is present with us this evening. So, during this week, we have a workshop. It's going to take place at the Abattoir Museum in Toulouse. And I'm now going to hand over straight away to Linda, who's going to describe this fabulous adventure that was the Cassini mission.
Merci. J'ai oublié de préciser tout à l'heure qu'après la présentation de Linda, il y aura donc un temps d'échange et de questions. Pour l'instant,
After Linda's presentation, we'll take some questions and answers.
Well, bonsoir. I'm very happy to be here and to share with you some of the exciting discoveries made by Cassini. I've been fortunate enough to have worked on the Cassini mission for almost 30 years. And that's the amount of time it takes Saturn to circle the sun one time. So I've worked on Cassini for 1 Saturn year. In fact, my oldest daughter, Jennifer, had just started kindergarten when I started working on Cassini. And now she's married and she has a daughter of her own. And those years have just flown by. Cassini orbited Saturn for 13 years, revolutionizing our understanding of the planet itself, of the ring system, of the 62 moons around Saturn, and the giant magnetic bubble that surrounds the planet. This is one of my very favorite pictures. Only a spacecraft like Cassini could take this picture. because you see Cassini is in a place that Saturn is covering up the sun. And you can see all of the rings, including the beautiful blue E-ring, and I'll talk a little bit more about this picture. I'm a ring scientist, so I really like pictures of Saturn's rings. In fact, when I first came to Toulouse with my husband Tom, we were here over the weekend, and we had a chance to go out to Carcassonne. And I looked, and they're working on an art project, and I noticed what looked perhaps sort of like Saturn's, reminded me of Saturn's rings on the outside of Carcassonne. And there were bits and pieces on the roof, on the walls, on doors, all over. And when we were leaving, Michel Blanc took us out there, and we had a wonderful day. As we were leaving, looked back, and you could just start to see what might end up being a set of circles, or I think of them much like Saturn's rings, on Carcassonne. You'd have to stand in just the right place, and these pieces then would connect into circles. Iannis already showed you this view of the solar system, of the planets. Saturn is the second largest planet in our solar system. Its atmosphere is made mostly of hydrogen. It's a giant ball of gas. There's really no solid surface on Saturn. And when you look at it, what you're just seeing is the clouds that go around that planet. It's 10 times further away from the sun than the Earth is, and I think it has the best rings in the solar system. Now, how big is Saturn? Here are the Earth and the Moon to scale and the distance between them. And if you put Saturn up, you see that Saturn would fit in between the Earth and the Moon, Saturn and the rings, truly a giant planet. If you made Earth into a tiny ball, it would take 764 Earths to fill up the volume of Saturn. Saturn, made mostly of hydrogen, is very light, and if you could build a bathtub big enough, Saturn would float. Here's now a view of the Cassini orbiter and the Huygens probe. Iannis talked about these a little bit, and you can see for scale, the Cassini orbiter is about 6.8 meters tall. That white antenna at the top is 4 meters in size, and it's through that antenna that we sent all the data back to the Earth. Cassini is powered by radioisotope thermoelectric generators. The heat from the decay of plutonium is turned into electricity, and that powers the entire spacecraft. You can see the Huygens probe on the front of the Cassini orbiter, and there's another view of it off to the side. It weighed about 320 kilograms, and we carried this probe because we wanted to understand and see what the surface of Titan looked like, as well as make measurements down through the atmosphere. Now, the instruments for Cassini were selected in 1990, and it took us 7 years to build the instruments, build Cassini and the Huygens probe. And during this time, my daughters were growing up, and we'd periodically go and watch and see how Cassini was being put together. And here I am with my daughter Jessica on one of the days where you could bring your children to work, getting a look at where we were with Cassini. Now, the Cassini and Huygens probe were named after two scientists. The Cassini orbiter was named after Giovanni Domenici Cassini, and it turns out that he actually came to Paris in 1669, and he liked it so much he even changed his name to Jean-Dominique Cassini, and he helped build the Paris Observatory. He's known for one of his many discoveries. He was very prolific at looking at the planets. He discovered a gap in Saturn's rings, this gap here, and it's named the Cassini division after him. And so we felt it was fitting to name our mission after this great scientist. Christian Huygens discovered Titan, so it seemed quite fitting to name the Huygens probe after the scientist who discovered Titan. Now, as Iannis indicated, Cassini is truly an international mission. And here are the flags of the 19 countries that provided instruments and hardware and scientists, and all of us working together to make the mission that became Cassini. And the European component was very important early on, because you see at one point in the United States there was some thought about canceling the Cassini mission. It was costing a lot of money. And so our European colleagues said, wait a minute, we're spending money building the Huygens probe, so we want Cassini to continue. So in a very real way, they rescued Cassini and kept the mission going. Now, I want to show you a little video of the launch. So here's a view of Cassini in 1997 for that launch.
T-minus 15 seconds. T-minus 10. 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. Pitch program is in, roll program is in. We have cleared the tower, and the Cassini spacecraft is on its way to Saturn. T plus 20 seconds. All systems are go. Jupiter Inlet Tracking Station now acquiring data. All systems go.
It was very spectacular to be there to watch this launch. In fact, we took our daughters out of school for a week so they could come with us and watch the launch. And they were very excited to go to Florida and be part of all of the excitement and watch the launch. Although what they found out once they got there is this launch, as you can see, was before dawn. And getting 3 teenagers up and out to see the launch, that was quite an accomplishment in those days as well. And I remember feeling the roar of the rockets, as you know, even though we were a distance away, you could literally feel it in your bones. And also watching as Cassini went up into that cloud, and the cloud got very bright. And everyone sort of held their breath and said, oh no, did something happen to Cassini? Because the cloud brightened, and then slowly Cassini came out from the cloud. And we knew that Cassini was on her way and all was well. Here's the Cassini mission against that 30-year orbit of Saturn. We launched in 1997, arrived at Saturn 4 years later in 2004, and then we had a 4-year prime mission arriving at Saturn just 2 years after northern winter solstice. I had a 2-year equinox mission where we looked at the planet with the rings edge on to the sun, and then a 7-year solstice mission with Cassini ending at northern summer solstice. And in that green box are the proximal or grand finale orbits, a chance to do something no spacecraft has ever done before. And that's to dive in between the rings and the top of Saturn's atmosphere and make incredible new measurements. And that was tremendously exciting. Here's another view of the Cassini mission. At the top by year, you can see the number of orbits. Below that are the number of flybys of Titan. We were very interested in Titan scientifically, but Titan also provided a way to change the shape and the orientation of Cassini's orbit. So you'll notice that we flew by Titan 127 times and got a good chance to study it. We flew by the tiny moon Enceladus just 3 times in the prime mission. But what we found was so amazing that we added an additional 20 more flybys of Enceladus, that this tiny moon was active with geysers coming out of the South Pole, so worth many more visits. Then we had 15 flybys of the other larger moons in the Saturn system, and then the final year, 22 orbits through that gap between the rings and the planet. At the bottom, you can see the change of seasons in the northern hemisphere on Saturn. Well, one way to watch the seasons change, you can actually look at where the shadow of Saturn's rings falls on the planet, and you can tell the season. If that ring shadow is in the north, it's winter in the north. So whenever the ring shadow falls in that hemisphere, it's going to be headed towards winter. At equinox, the ring shadow is so small, it's just a line right at the equator. And toward the end of the mission, the ring shadow moved to the south, and so winter moved to the south around Saturn. One of the early surprises is that when the ring shadow covered up Saturn, that golden atmosphere suddenly looked very blue. Those haze particles that grew high up in the atmosphere slowly disappeared when there was no sunlight to keep generating them. And so Saturn started looking a little bit like Neptune in the northern hemisphere. And as the seasons changed, that bluish color started to disappear little by little, and the southern hemisphere started to become blue. And there's a view of Titan in front of Saturn. Here's that view of Saturn again, and if you look carefully, you'll notice that there's a very interesting shape right at the North Pole. It's a six-sided jet stream, a hexagon that's present on Saturn. Here's a close-up view of that hexagon. It still has that blue-greenish color from the winter. That hexagon is so huge, it's 2 Earth diameters across. And the clouds on the edge of the hexagon go racing around. That jet stream is just like a jet stream on the Earth, only it has stayed like this since the Voyagers first discovered it in the early 1980s. Why does it have 6 sides? Why has it stayed that way for so many years? We don't know. It's the only 6-sided jet stream, a jet stream that looks like this in the solar system. Here's a movie of the hexagon. You can see the clouds racing around very quickly. This is in false color, very quickly, like horses on a racetrack going around inside the hexagon. And at the very center, there's that reddish feature. It turns out that Cassini discovered a giant hurricane right on top of Saturn at the North Pole. This hurricane's about 50 times larger than a typical Earth hurricane. In this view, the sunlight's coming in from the right, and you can actually see the shadow of the eye wall inside this giant hurricane. Cassini was also at the right place at the right time. In late 2010, a giant storm formed around Saturn. That storm was so huge, it grew a large tail that wrapped all the way around the planet. And when the head and the tail came together, the storm started to disappear. This storm lasted about 9 months. Storms like this happen only about once every 30 years. About once every Saturn year, you get this huge eruption on Saturn. And for Cassini, this storm came about 10 years early. So he had a chance to study this storm at different levels in the atmosphere. Looking in the near infrared, you're looking deeper. Now you can see that greenish cyclone that was basically the eye of the storm and from which the tail grew behind it. If you look in the far infrared, you look higher up in the atmosphere, there's a lot of energy coming up from Saturn, and you can see what looks like a giant cyclops eye. And a lot of chemistry happened because it was very hot in this region, and it took a couple of years to cool off. So very interesting to watch this storm in particular. Lots of lightning along with it and other interesting things to study. And we worked with our ground-based observers also because Cassini couldn't look at Saturn every single day. And so they helped us put together the story of this storm. Here are Saturn's rings. They have simple names, A, B, C, and then the innermost tiny D ring, jumping out the E ring, F ring, and G ring. And the rings are just named in their order of discovery. Galileo actually was the first person to see the main rings around Saturn. He thought they looked like 2 cup handles or ears around the planet. Here's another view of the rings. The rings actually are not, they're made mostly of water ice particles that range in size from tiny dust grains to particles as large as mountains. But there's a little bit of non-icy material, probably from micrometeoroids coming in and hitting the rings and causing sort of a pollution across the rings and giving them a color. And the thinner the rings, like the C ring and D ring, don't have many particles, so they are grayer and have more pollution. And here you can see the Cassini division as well as the Encke gap, and just really incredible detail from the Cassini pictures. Now, some people wonder, where did the rings come from? How did they get there? Did a moon get too close to Saturn and break apart? Did they form at the same time as Saturn formed? Well, there's some scientists who think that perhaps The rings are made of lost airline luggage. If you ever lost your suitcase, who knows? Maybe it's out there circling Saturn. And this is from a T-shirt that I have that someone put together after the Cassini mission. Here's a view of Saturn and the rings at equinox. The sun is exactly edge on to the sun. And anything that sticks up or above or below the rings, they're only about 10 meters thick, would cast a shadow. So here is our chance to see, are the rings perfectly flat or are they warped a little bit? Where could we see three-dimensional structures in Saturn's rings? And this doesn't occur very often, just twice in a Saturn orbit. So once every 15 years, the sun is edge on to the rings. And when we look from the Earth, we really can't see the rings either. But Cassini was up above the rings, looking down, trying to find these shadows. And in particular, we took some pictures on the outermost edge of this bright ring, the B ring, and here's what we saw. Lots and lots of spiky shadows created by objects in this 10-meter thick ring that are half kilometer to a kilometer in size, and that basically like cars on a freeway crowded together at the edge of the B ring. And a good analogy is, imagine you're in the space station and you want to find the pyramids. If you look down to find the pyramids at noon, their shadows will be very small, and it'll be very hard to see them because they'll blend in with the background desert. Now imagine you look for the pyramids at either dawn or dusk, the equivalent of equinox. There, there'll be long shadows and easy to pick out. So in this way, we could find special places in Saturn's rings that cast shadows. And I think this is a really very beautiful picture, and we're puzzling about, why do you get such big particles, almost like little moons, just right there at the edge of the B ring. Another thing Cassini discovered was a very bright feature at the outer edge of Saturn's A ring. You can see that feature, and it's blown up here, and it appears that there was maybe a 3-kilometer sized object, maybe a tiny little moon nicknamed Peggy, that was right at the edge of the ring. And so we started watching. This feature appeared in April 2013, and we kept going back and looking to see if Peggy might break free and become a new moon in the Saturn system, or perhaps go back into the rings and perhaps be broken apart. And even at the end of the mission, we could still see evidence of Peggy, but we didn't see a little moon break free. So maybe the next mission to go back can look and see what might have happened to Peggy. Here's that beautiful picture I showed you in the beginning. It's just so incredible. Only a handful of times during the Cassini mission were we in a place where the Saturn covers up the sun. And if you look around the edge of Saturn, you can see a bright white circle. The light from the sun comes around, is refracted through the atmosphere. And if you think about it, that's every sunrise and sunset on Saturn seen at the very same time. And with the sunlight shining through the tiny particles in the rings, if you've ever driven your car with a dusty windshield into the afternoon sun, you know it gets hard to see. Those tiny particles scatter that light forward into your eyes, and they just glow. And if you look at the night side of Saturn, it's not dark. Instead, light from the rings is reflecting onto the night side of Saturn. So there's just a lot of very interesting things to see. And there's also 3 other planets in this picture as well. If you look carefully, you'll see Mars, Venus, and the Earth and the Moon. And we took this series of pictures in 2013, and we asked people, it was in July, and you could see the Earth at the time, you could see Saturn at the time Cassini was taking the pictures, from the west coast of the United States all the way across Europe. And so we said, okay, go outside and wave at Saturn while we're taking the pictures with Cassini, and so your photons, you'll be in that little picture that's taken of the Earth. Now, of course, it's very tiny, the Earth and the Moon. You can see here, the Earth is blue, but it's very little. So he said, take a selfie. Take a picture of yourself waving at Saturn and send it to us, and we'll recreate this very beautiful mosaic. We got thousands of pictures from all over the world. people with their dogs waving, their families, clubs, groups, everyone together. And so we did take those pictures, and from those selfies, recreated that picture of Saturn. This was very popular because everyone wanted to go and find their picture somewhere, and it might be more than once, because if we had to, we used it more than once. And I know that Tom and I were waving at Saturn, and I went and looked till I found our picture in this particular mosaic. Just a little bit about some of the moons at Saturn. There are 62 moons in total. Many of those are far away from Saturn. They're probably captured objects, maybe from the Kuiper Belt. This just shows some of the moons. Titan is clearly the largest. In fact, if you look at the 4 inner planets, Titan is about the size of the planet Mercury. And had Titan formed anywhere else in the solar system, Titan would have been a planet. But just a very interesting and very large moon. Here's another unusual moon, Iapetus. We knew from Voyager and from the ground that Iapetus had one side as bright as snow and one side as dark as charcoal. And we wondered, is it material coming from inside Iapetus that's dark coming out, or is something outside coating one side of Iapetus? And you can see that very dark side, and it gets very bright toward the pole. And it turns out that another moon, Phoebe, far away, the dust from Phoebe comes in and is coating just one side of Iapetus. Iapetus also has a huge ridge. It looks like a giant walnut put together, and that ridge is very, very old. Maybe Iapetus had a ring, and the particles from the ring fell back on the equator and formed the ridge. We don't know, but it's very old because you can see craters have broken apart that ridge, so that's probably hundreds, probably billions of years old around Iapetus. Just want to show you something about the tiny moons, we call them ring moons, that orbit very close to the ring. So I'm going to take that region of the rings in the A ring where the blue arrow is and blow it up. And there you can see the Encke gap with the moon Pan inside of it, Daphnis in the Keeler gap, and Atlas at the outer edge of the A ring. And it turns out that both Pan and Daphnis are big enough that their gravity pushes apart the rings and keeps that gap open. Now, if you look at these 3 side by side, what you'll notice is that each of them has a ridge of material, like a giant skirt. They've accumulated ring particles until they're at the point where Saturn's gravity and the moon's gravity just balance, and the ridge can't get any larger. There's a central body. You can see that the moon Pan has a bigger round object in the center of it compared to Atlas, but Atlas has a much bigger, fluffier looking skirt of ring particles around it. And Daphnis might even have evidence of 2 ridges, one here and one here, picking up these ring particles. So if you're close to the rings, you're going to look like a very unusual moon. Here's another one of my very favorite pictures. Not only does that moon keep the gap open, it creates this beautiful wave along the edge of the gap. And you can see that by the 3rd wave, the ring particles are actually separating. It's both a horizontal and vertical wave along the edge of the gap. And with these orbits getting in very close to Saturn at the end, we could see incredible detail here. This is a view of Titan. This is the view that Voyager saw, a moon that's just covered with this thick haze like a smog around it. And that's what led us in the 1980s to start to think about let's go back and let's carry a probe. As Iannis indicated, here are the stages of the probe. Once the heat shield had slowed the probe down enough, then a series of parachutes opened up, and for 2.5 hours, Huygens floated slowly down to the surface of Titan. Now, we didn't know for sure if Titan would be covered with a global ocean of methane or not, so the probe was built to float, at least for a few minutes, in a liquid methane ocean. Huygens soft landed on the surface of Titan, and as Cassini flew overhead, continued to send back data for another 1.5 hours. And we also got a radio signal linked to the Earth, and it took about 6 hours until the batteries had cooled and Huygens stopped sending back data. Now I want to show you a movie of the pictures taken as the Huygens probe descended down to the surface. You could see evidence of what looked like river channels or dendritic flows, mountain ridges, slowly piercing through the haze, and then ultimately with the Huygens probe landing on the surface. And this is what Huygens saw as Cassini flew overhead for that additional hour and a half. Rounded icy pebbles. We had landed in a dry stream bed or lake bed that flowing methane had rounded these pebbles. Turns out that methane plays the role on Titan that water plays here on the Earth. You can have methane clouds, methane rain. Methane can create river channels and flow into lakes and seas. So methane, it's just at the right temperature on Titan to have this methane cycle be active. Here's a view coming down from the top of the atmosphere to landing on the surface. And here are some of the dimensions of some of those icy pebbles that we saw. And in that middle panel, just a comparison, here's a footprint on the moon to give you an idea of some of the scales on Titan. And then many of these river channels flowing down into the region where Huygens landed. If you look carefully at Titan's North Pole, you see a region here of dark splotches. These are the giant seas and lakes on Titan. And we didn't know for sure if it was a liquid or not, but we knew methane could be a liquid at those temperatures until we saw this signature. If sunlight hits a liquid, it gets reflected off at the same angle, you get this scattered point, and it's very bright. So this specular reflection told us that there was indeed liquid in the lakes and seas. Here's a radar view. We had a radar mapper that could pierce through the haze. You could see the river channels flowing into it. This is Ligeia Mare. It's about the size of the Great Lakes on the Earth and about 300 meters deep. And if you added up all of the liquid hydrocarbons on Titan, you'd have about 55 times more hydrocarbons on the Earth. If only we could build a giant pipeline all the way to Titan, our hydrocarbon problems would be over. A little bit about the moon Enceladus. Enceladus is 1/10 the size of Titan, only 500 kilometers across. But it looks very different from many of the moons. It looks very bright and young and icy. And there are places where there are no craters at all. So some process has filled in those craters. We noticed 4 bluish fractures, tectonic fractures we called tiger stripes, and we wondered about those. When Voyager flew by Enceladus in the early 1980s, the South Pole was in darkness, and so we missed seeing the tiger stripes. Here's a close-up view of one of those tiger stripes. They're quite long. They're over 100 kilometers long, about 2 kilometers wide, and you can see what looks like frost on the edge of that tiger stripe. And that's because coming out of those 4 fractures are actually jets or geysers of water ice particles and water ice vapor going out into space. In fact, there's over 100 individual jet sources coming out of these 4 fractures, perhaps with curtains of material coming out as well. Now, the reason we added so many extra flybys of Titan was to be able to fly through the plume with Cassini and to directly sample the composition of the particles and of the vapor. When we did that, here's a backlit view of some of those jets. Now you can start to see individual jets. We found out the water was salty. We also knew that Enceladus had a global ocean of liquid water, and so it's very intriguing to find conditions not unlike the Earth's oceans. Now there's a place here on the Earth that's named Enceladus as well. And it turns out that that fountain is at Versailles in France. This is the Enceladus fountain. Enceladus was a giant. He got into a bit of trouble with some of the gods, and so they threw him down into Mount Etna. And so here Enceladus is trying to escape from the lava of Mount Etna, and he has this giant stream of water 25 meters into the air. And when I first went to Versailles, I took this picture. I'm like, look, it's Enceladus here in France. So here's a giant Enceladus. Most of the particles fall back onto Enceladus' surface, and that's why it's so white and icy. But some of the tiniest particles escape, and look like wispy fingers coming from Enceladus. Enceladus is the black dot. Here's the plume. Here are some of those particles escaping to space to form the ring, the E ring, that goes completely around the orbit of Enceladus. Here's what we think the inside of Enceladus looks like: a global ocean, perhaps with hydrothermal vents on the seafloor. We think there are active hydrothermal vents because there are tiny grains of silica, nanosilica, that can only be created at very high temperatures. We think that the cold water mixes with the rocky core of Enceladus, gets heated up. When it comes back and encounters the cold water, those grains can condense and come out the plume. There's also an excess of hydrogen. Now, we know a lot about hydrothermal vents because we see exactly this kind of process happening on the seafloor of the Earth. Very deep, there's no sunlight. It's at a place where the seafloor is spreading apart, and this cold water mixes in with the hot material of the Earth's crust, comes back out, and those little particles condense and looks like plumes of smoke. If you first looked at this, you might think this was a giant fire, but this is deep in the Earth's oceans. What we find around these hydrothermal vents, where there's no sunlight at all, no energy, is that it's teeming with life. You find crabs and tube worms and all kinds of exotic life are just around these hydrothermal vents, islands of life that are using the heat and the nutrients coming out of the hydrothermal vents. So it makes us wonder, could the ocean of Enceladus perhaps harbor life as well? And that will take a future mission to go back. Cassini didn't carry any instruments to look for those big molecules like DNA or any kind of chemistry that would tell us that life might be there. Well, now I want to talk about Cassini's grand finale and goodbye. It turns out that we went into this set of orbits because after discovering the potential for life on Enceladus, and there's methane seas on Titan, astrobiologists wonder, could you have a very unusual kind of life that could form in the liquid methane? So as Cassini was running out of fuel, we had to find a way to make sure that Cassini would not crash into Enceladus or perhaps into Titan, because you see the radioactive material is warm, and we didn't sterilize Cassini. We didn't know we would have to do that. We don't want to take any chance of bringing Earth life down to one of these moons. So this is a view of Cassini flying through that 2,000 kilometer wide gap between the top of Saturn's atmosphere and the outermost ring. And it's just incredible discoveries coming out of it. In fact, the meeting I was at this week, here's a picture of all of those people attending the meeting. Scientists gathered from around the world here at a meeting in Toulouse to talk about what might be going on in that region in between the planet and the rings. And it turns out all kinds of interesting results about what might be happening, and they're busy writing papers and coming up with models. The takeaway message is all the things we thought we knew, those models were too simple or not right. And so the scientists are very happy. Whenever their models don't work and they have to start over, that makes a very, very, very happy scientist. Here's what some of those orbits look like, 22 of them passing in between the rings and the planet. And we had to share, sometimes we looked at the rings very close, sometimes the planet, and always trying to position our instruments that measured the particles and fields so they could be able to take data. And so we had 22 of these orbits. Each time Titan would move us around a little bit. We started out close to the rings, slowly moved in close to the planet, until on that final red orbit, we got a nudge from Titan. Titan was far away, but we call it Titan's goodbye kiss that sent us on into the atmosphere of Saturn. Now imagine yourself holding on to that white high-gain antenna. And what would it feel like? What would it be like to fly with one of those orbits? And here's an animation that shows you're coming in. This whole 15 seconds is covering only an hour of time, very close to Saturn, and back out. And every 6.5 days, repeating this flyby over and over, and you can imagine the Cassini instruments turning right, turning left as quickly as possible. And I'm a big fan of Star Trek, so I kind of imagine maybe this is what it'd be like to be on the deck of the Enterprise, flying between the gap and the rings. On one of the first orbits, we made this movie. We pointed the camera. You can see the red dot moving along on Saturn. We got views of clouds at much higher resolution than we'd ever seen before. These are in our clear filter, wide-angle frames, and yet they were a little more than a postage stamp. As the frame turns, on the first orbit, we used the high-gain antenna like a shield to protect us in case there were big ring particles in there that could damage Cassini. Turns out all the particles were small, and Cassini was fine. Here's a view of some of the clouds on Saturn. One of the people who had studied Saturn and the giant planet said he'd never seen clouds quite like this ever before. There's a lot of new information about how the clouds form and how the weather works on Saturn itself. A little over a day before we went into Saturn's atmosphere, we took this final set of color images of Saturn in the rings. And so this was our farewell mosaic to the Saturn system. Now, the end happened very quickly for Cassini. This just shows the final 90 seconds of the mission. We were gathered starting about 4 in the morning to watch that final signal coming back. And it turns out, here's what we saw. On the top is X-band, the bottom is S-band, 2 different radio frequencies. What we saw is first, the movie will repeat, first the X-band signal at the top, which is that spike that sticks out of the green, that spike. It disappeared, followed a few seconds later by the S-band signal. And at that point, we knew, it was about 5 in the morning in California, that the Cassini mission had ended. And I'll tell you, it's really hard to say goodbye. And you can see here some of the people, hugging each other and just reliving sort of that final moment for Cassini. And it was really, we had people from around the world watching us as well for Cassini. And here's the Cassini family waving goodbye on that final day. It was a tremendous group of people. If you think about it, people that have been together for decades. We've gotten to know each other, we've taken vacations together, and our kids have grown up together. And I actually had my family, I had Tom and my daughters, Jessica and Jennifer, and granddaughter Audrey, there for her first big spacecraft event for the end of the mission. And what an incredible mission, what a tremendous privilege I feel to have been part of going to a place that we didn't know very well. And we really had a rare opportunity for collaboration as well, and we seized it. What I'd like to do is show you a movie. This movie is sort of a synopsis, a summary of all of the discoveries of Cassini set to music. So enjoy. when I see that movie, I think, I want to go back. Thank you very much.
Thank you very much, Linda. Thank you so much, Linda, for this exciting presentation. Donc, on va passer aux questions et aux échanges voilà, après cette brillante présentation. Donc pour
Move on to the questions after this brilliant presentation. So for our public next door too, ask Iannis to come onto the stage too. So if you, there are mics going around the room. I have one here too. So we suggest that if you want to ask any questions on the missions that you've just seen, on science in general, either in French or in English, in any case it will be translated. Good evening. Linda.
What's next? Well, I hope we can have a mission to go back to perhaps Enceladus or Titan to complete and do further studies, maybe send a probe into Saturn's atmosphere. But I also know that we haven't studied Uranus and Neptune very much. So it might be nice to have a mission to go back to Neptune or to Uranus.
Hello. What would you say is the biggest unsolved mystery about Saturn yet?
The biggest unsolved mystery about Saturn, I think perhaps it might be tiny Enceladus. There's so much we don't know about those geysers coming out of Enceladus. And then close behind it is Titan, those liquid methane seas, and how did Titan get this thick methane atmosphere? It's almost like it has a runaway greenhouse effect to keep the atmosphere warm.
Hello, thank you very much for your presentation. It was outstanding. I'd like to know if you had unlimited money to do a space probe, and you would be interested in the rings, and how would you do to date, to make the datation of the rings, to know if they are old, like few million years, or very young, like few thousand years? I don't know.
Yeah.
How would you do?
Well, to answer that the second question first, we think the rings are young, that we've been able to measure in these final orbits the mass of Saturn's rings. We think they're only a few 100 million years old. If you think about it, dinosaurs were roaming the Earth perhaps at the time Saturn's rings formed, the rings that we see today. And if I could have any amount of money, I would probably go back to Saturn or one of these planets, and I'd take a Saturn probe, perhaps even a balloon or a boat to float in the lake of Titan, a probe to go down to the surface of Enceladus, and maybe even bring a sample of that material back to the Earth where we could really do a good study about whether or not there might be life, maybe a sample from Enceladus and a sample from Titan. Oh, and for rings, there's another very interesting concept where you could actually have a mission that could hover over the rings and imagine making movies of those ring particles in a very intricate cosmic dance around Saturn as they bump into each other, perhaps stick together. And so you could add that as part of your mission as well.
Une question là-bas.
Question over there. Good evening. Yes. So, Julien, is the fact that you didn't detect organic molecules on the flybys of the geysers, for example, does this reduce the chances of detecting life?
I think your question was, we didn't see any big molecules on Enceladus. It turns out that we didn't have the instruments to measure big molecules. We could only measure up to 100 atomic mass units, equivalent of 100 protons or neutrons. So those are pretty tiny molecules compared to DNA or very complex chemistry that would happen for life. So we'd need to go back with an instrument that could measure maybe 10,000 or 100,000 times bigger molecules to answer that question. Or take a sample, get a sample and bring it back.
J'ai une question.
I have a question. You showed a very broad panel of international cooperation involving a lot of different countries. I think it's 19 in all. You were the scientific manager for the mission. How did you manage? Were there trade-offs to be done over that period? You had to make choices. You didn't always get the performance that you wanted. How did you experience that? How did you manage it as the scientific manager?
That had to be made, and sometimes it's not always easy with scientists to get them to agree on what you would want to do. And one of the philosophies we use is everyone is equally unhappy. Then you found the right balance, because obviously you cannot make everyone happy at the same time. And sometimes trades were driven by how much budget did you have? How much time or schedule did you have? So you have to fold that in as well.
Hello, and thank you again for the talk. I was wondering if Cassini helped you or not to discover more moons of Saturn, because I remembered 50-something moons and just discovered there are 62. So did Cassini help you discover new moons? I saw you were talking about Peggy, that will be maybe one day another moon of Saturn. So Cassini helped you about that?
Cassini did discover a number of new moons. Daphnis in the Keeler Gap is one of those. And there's some other tiny moons in between the larger moons. And in some cases, tiny moons actually share an orbit with a bigger moon. So Cassini did discover many new moons in the inner part of the system. At the same time, some of those moons in the outer part were still discovered by ground-based observers.
Thank you.
Moi, j'ai une question pour l'IRAP.
I have a question for Iannis. We saw you intervened on this mission. Could you just say a couple of words on cooperation with IRAP in Toulouse, with NASA? Is this the first time you cooperated? Could you say a few words on that? Exactly. There was a lot of cooperation with the Mars Science Laboratory. So there's a whole suite of cooperation, and Cassini is just one example among others. So that was the first time you cooperated with NASA, was it? Not with NASA, because there are other missions. There were missions, terrestrial missions, for example, with probes. The International Sun-Earth Explorer, for example, with 2 probes orbiting the Earth to study the Earth's magnetosphere. And then there were international experiments. In particular, we had one devoted to, in Berkeley, and some of the work was developed in Toulouse. So this was done back in the 1970s, and it was actually launched in 1977 on a NASA mission with cooperation from ESA. So we were used to working with our American friends and colleagues. And of course, with Cassini, this took on a new dimension, because this is the first time that we've been onto a giant planet together. Thank you for the presentation. Linda, you're continuing to work on Cassini to process all the data you've got, but are you still working on that personally, or have you moved on to something new? And how does that transition, if you are working on something new, how does that transition work?
Well, I am working on Cassini data. I'm a member of one of the teams, the Composite Infrared Spectrometer team. We have a lot of good ring data, especially from the last year of the mission. So I'm looking at those data. But I'm also thinking about transitioning to maybe NASA has different missions, Discovery, New Frontiers, to maybe be part of a mission to go back to Saturn, get it started, and maybe get it launched, and then watch, maybe as my children or my friends' children work on these future missions.
D'autres questions? Alors, vous allez...
Another question?
Nombreux ce soir, donc,
There's plenty of us here this evening. I'm sorry for people in the other room at IMAX, who aren't in a position to put questions. I've got a question for both of you. In Linda's presentation, we heard that there were gaps produced by the moons. How can you explain the size of the Cassini division?
The size of the Cassini division is a very interesting question. It turns out that the outer edge of the B ring is confined by what we call a resonance with one of the moons with Mimas. Mimas is quite a large moon. Just means that the particles at the edge of the B ring go around exactly 2 times for each once for Mimas, and so that boundary is held firmly in place. Why the inner edge of the A ring falls where it does, that we're not sure about. That's the inner edge, that's in between. The Cassini division is in between those 2. But Mimas is holding the B ring in. Otherwise, the rings, we think, would just keep spreading outward and inward.
Yes. Linda explained very well, yes.
D'autres questions?
Other questions? Take advantage of this because Linda...
Back tomorrow, I think, to the United States. So, also une question.
Did the mission learn new things about the internal structure of Saturn and the coupling with the magnetosphere and the solar wind?
Yes, in these final orbits, we learned a lot about the interior of Saturn, its magnetic field, its gravity field. The winds seem to go very deeply into Saturn. The magnetic field axis and the spin axis of the planet are almost perfectly aligned, and that's hard to explain to maintain a magnetosphere. So many interesting puzzles, and we learned a lot of new things, still calibrating and trying to understand and model the data. And maybe Iannis wants to say something about the MIMI data.
Exactly. What happens is that the magnetosphere of Saturn has an interaction with the solar wind, which is very different from that of the Earth. On Earth, the solar wind just governs the dynamics of the magnetosphere. On Saturn, we have Enceladus, which taking out plumes and a lot of neutral gas, which interacts, is ionized, interacts with the magnetosphere, and we have a lot of neutral ion interactions.
Hello. So, we have, you told us about the data analysis. So you still have a lot of data to analyze. What great discovery you hope to have in the future?
As we continue to analyze the data, perhaps we'll get an even better understanding of what the inside of Saturn is like. And that would perhaps tell us how Saturn formed and maybe how the planets in our solar system formed as well.
Une question. Quelle est la taille?
Another question, what is the size of the particles in Saturn's rings? In other words, a histogram of the particles making up the rings.
In Saturn's main rings, the particles are mostly in the millimeter to centimeter, maybe tens of centimeters range, the bulk of the mass of the particles, although there's some tiny dust grains and then just a few of the much larger particles, but millimeter to tens of centimeters, typical particle size.
Bonsoir, merci pour la présentation.
Good evening, thank you for the presentation. Is the rotation of the gas around Saturn depend on the altitude, and if so, is the presence of the hexagon indicate that there's a certain zone where the rotation is exactly the same? And how can this be explained?
The gases on Saturn at different latitudes rotate at different rates. And then there's convection deeper into the atmosphere. The hexagon, why it has 6 sides, why it rotates faster than the atmosphere outside and inside, that is an interesting puzzle, and just how deep it goes, we're not sure.
Plus de questions?
No more questions? You showed us pictures of the North Pole of Saturn with this hexagon, this vortex. If I remember correctly, the probe that's now around Jupiter showed us that the North Pole of Jupiter, and the South Pole too, has the same phenomenon of a hexagonal vortex. Is that correct, or am I mistaken? And is there a relation between those two different vortexes, or vortices?
At Jupiter, we don't see a strong jet stream hexagon. There are some interesting storms at the North and South Pole that appear to form patterns that might look like pentagons or hexagons. At Saturn, the South Pole has a hurricane, but it has no hexagon. Its jet stream there is, everything is circular at the South Pole.
I'm sorry to ask too many questions, but I would like to know if I were on Saturn, okay, during summer, during the nights, I would see the rings in the sky. How bright it would be, like 2 times the full moon, or brighter even?
Yeah, it probably would be something like the full moon, depending on how much of the rings were sending light back. As the seasons change, the rings are brighter and darker as well. So in the summer, when the rings are brightest in the north, that would be the brightest on Saturn.
Alors, est-ce qu'on a épuisé toutes les questions?
So if we've exhausted all the questions, I think we can let our speakers take a deep breath. But we're pretty much running according to our timing here. Here we've got a question. Is spectroscopy able to detect bigger particles on the geysers, as with solar light spectroscopy, for example? On Encelad, the question is on Encelad. Would you be able to detect it on Encelad?
We can look in the visible wavelengths and actually a range of wavelengths and get an estimate of the size of the particles. And they tend to mostly be micron in size, although there are bigger particles that just go up a short distance and fall back. So you can use visible light, and then also our particle detector, our cosmic dust analyzer, can measure the mass of the particles as well, and get a size from that too.
Good evening. Have we an idea of the size of the solid nucleus of Jupiter, I think you said, which apparently holds the gas around the planet? I think he said Jupiter. He said Jupiter. I don't know if he's talking about Jupiter or Saturn, in fact, but he did say Jupiter. Saturn. Okay, Saturn. Yeah, okay.
But certainly it looks like that core inside Saturn is many Earth masses. I think it's larger than we expected. We're still looking at the data and writing the papers, but many Earth masses.
Question.
If Cassini had more fuel, would you have extended the mission, or would you have been obliged to end the mission because of the risk of a major failure on board?
Well, the Cassini spacecraft was very healthy, and had we had more fuel, we would have certainly extended the mission and looked at Enceladus some more, looked at Titan, flown closer to some of the other moons. So we had a very healthy spacecraft. We were just running low on fuel.
Si je me souviens bien, on avait...
If I remember correctly, we were very surprised when the landing took place by the winds on Titan? Have we understood all the tidal phenomena on these different satellites?
For Titan, we're still working to understand the winds and the weather and what tides might be raised by its interaction with Titan. Same thing is happening for the other moons. It's interesting, in the case of Enceladus, it was because Enceladus, it wobbles as it orbits. Its libration was greater than it should have been for a solid body. And that allowed us to say you had to decouple the crust and the core, and you could do that with a liquid water ocean.
Bonjour. Tout à l'heure, vous avez...
Good morning. A little earlier, you specified that it wasn't run with solar arrays, but a motor, an engine. Could you explain the operation, how the thing was, of the magnetosphere? No, of the motor that allowed the RTG to be supplied.
Moving parts in the RTG. It just took the decay of the plutonium, the heat from that decay, and with thermocouples could turn that into electricity, and it really wasn't a lot of electricity to run the whole spacecraft. And as the mission progressed, there was less and less decay of the plutonium, so we had less and less power, and we had to more carefully manage and take turns about who could be on at the same time.
Bonsoir. Est-ce que vous avez connu un moment vraiment...
Good evening. Did you have one critical moment during the Cassini mission?
I think there were a few critical moments with Cassini where we expected Cassini to be sending a signal back to the Earth, and something had gone wrong. In a couple of cases, it might have been a bad command. In one case, especially in those last orbits, we didn't hear from Cassini after it had made one of its plunges, and we thought, oh no, did we lose Cassini? But it turns out it was a problem with the station receiving the signal. So those, when we don't talk to Cassini, if something goes wrong, Cassini turns off all the instruments, shuts down all the non-critical systems, kind of just like curls up and says help, and just sits there and waits until it hears from the Earth.
Il a été évoqué plusieurs options de fin de mission pour Cassini.
You told us about several options for the Cassini last mission. One of them would be to use the remaining fuel to go to Uranus or Neptune. Why didn't you do that? Because you just said that it would be interesting to explore these two planets.
At the time, we had to decide between going with the grand finale or maybe going to Uranus and Neptune. We would have missed a lot of flybys of Enceladus and of Titan. And Cassini's instruments were really designed to study Saturn. Plus, that mission to Uranus or Neptune would be very long, and we would have that much less power by the time we got there. But there were so many questions left in the Saturn system that the scientists unanimously said, let's stay, let's do the grand finale.
Thank you very much. Bonsoir.
Good evening. I know you have boreal dawns on Jupiter. Do you have them on Saturn and Jupiter? And if it's the case, could you observe any?
What were there on Jupiter?
Des aurores boréales, comment tu dis ça?
Aurora borealis.
Aurora.
Auroras, yes, sorry.
We did see aurora on Jupiter and on Saturn as well. Saw some very extensive aurora and actually could see the footprint of Enceladus by the connection of the Enceladus field lines to Saturn as well. So both planets did have aurora at both the north and south poles. What's interesting with Cassini is we could look at the aurora with Cassini and also look with Hubble at the same time and sort of get a stereo projection by looking at the aurora from two different directions.
J'ai entendu dire que dans les
I heard that during the Mars missions, you use atmospheric drag to orbit around Mars. Do you think it would be possible to do the same on Saturn?
With Cassini, we couldn't use atmospheric drag because there were so many pieces sticking out all different directions. But you could design a spacecraft, maybe if we go back to Uranus or Neptune, could use what we call aero capture, slow down using the atmosphere of the planet and have to carry less fuel. So that could be a possibility for a future mission.
Hello. Here. Hi, thanks for being here. If you were to go back on a new mission and find some kind of life or some potential, what would you do?
If we went back with a future mission and thought there might be life there, then there might be a need to go and get a sample, to bring the sample back to the Earth. But then we'd have to be very careful not to let that life contaminate anything on Earth or to get Earth life in with it. So we would be very careful with how we maybe handled the sample in space or something. But if we thought we saw evidence for life, the right answer is probably to go get a sample, bring it back, and use all the technology and the instruments on the Earth to look at it. We think it's probably going to be very small, little life. We're not expecting fish or anything like that.
Bonjour. Voilà, je voudrais savoir.
Good evening. I'd like to know whether Saturn's speed is constant, and if not, can it have any impact on the rings, on what happens on all Saturn's rings? Could they agglomerate? Could they mix? Well, I mean, all these particles in these rings. If the planet slows down, what could happen to the rings?
Right. The rate at which Saturn rotates isn't affecting the rings. It's just the mass of Saturn. And the rings are in a very special place where they can't come together and form a moon. They're inside something we call the Roche limit. And so they get torn apart and can't grow into anything big. We were surprised to see the two tiny moons, Pan and Daphnis, there in the rings, because they're inside the part of the Roche limit as well. But we don't think the rings can come together. They'll probably, like pouring water on a table over time, they might just spread out in both directions, although their outer boundaries are held in place by resonances with moons.
Bonjour. Au niveau organisation.
Good evening. For the organization of the mission, once the primary mission was done, did you automatically switch to the prolongation, or did you have to fight to get extra budget to continue your mission? Mission ended when there was no more fuel, but it could also have ended because lack of money. Was it difficult for you to continue till the end?
You're right. We had to make a proposal to NASA, telling NASA what we would do next for the science. And then NASA had to decide if they were going to give us more money and exactly how much. We put in a proposal, like a bid, for an extended mission. And the first few were easy, but as we got further along, it got harder. As you're there a longer time, you have to be more and more creative about the new science that you can do. And once we had the grand finale, then I think NASA had to agree. We had to finish that.
Bon, on va peut-être en rester là s'il y a plus.
Right, so we might stop now because time flies.
Thank you very much again for this very, very interesting conference. Merci vraiment à nos deux conférenciers.
I would like to thank our two speakers.
The next step here is 5 of May, because there will be the launch of InSight mission, I think. So it's also a great event on the cooperation also between France and the United States. So there will be a teletransmission here at la Cité de l'Espace, 5 May. And there will be a big event during the evening of the 23rd of May also to come back on Mars mission, Mars cooperations. So you will be invited again. Thank you very much again.
Yes, very well.
And bonne soirée à tout le monde.
Merci.